Hello everyone. So let us understand one more problem from CodeChef Starter 2021. The problem name is Melancholy of Problem Setup. So you are given a tree with n vertices and a string C of length n consisting of the characters R, G and B. So you're given a tree and n vertices are there and every vertices correspond to a color that is R, G and B that is given to you as an input of a types like as input of a type string named C. Fine. Now each integer I, that is Ci, is the color of the vertex I. So the string C denotes that if there are 10 vertices, then the ith like character in that particular string denotes what's the color of the ith vertex. Now the input is called valid if all pairs of blue vertices, just focus that if the input is valid, the input that is the C string is valid, if all the pair of the blue vertices from the tree, there is at least one red and one green vertex on the simple path between U and V. So on a tree, it states that there is always one path that exists between any two vertices. So if you take every pair of blue vertices on that tree, there should be at least one red and one green vertex like in that path in every two like in every pair of B vertex. If there exists, then the tree is valid, else the tree is invalid. Can you tell that for the given input whether the tree is valid or not? That's the whole problem. How can you do that? Okay, let us take one example. I'm not taking any example from here, that is the input, but I'm just talking out or trying one example. Okay, let's take it like this. Okay, so let's say that if you take this as blue, okay, then if this is, let's say, green, this is red, okay, then this is blue, then this is green, then this is red. So there is only one pair of blue vertices, as you can see, this, that is this and this. So the simple path between them is this. So okay, and then what you can see here is, because this is a simple path between these two pairs, like these two B's, then there is at least one red and one green in their paths. The answer is correct, that this is valid. Fine, that's the whole thing. How can you do that now? Like what's the problem thing you can do that? You can pause this video, try to think over that. Now what's the biggest, like what is the observation? What you can see here is that, okay, let's say that what is the case in which there isn't any like green or red like a vertex inside that. It can happen that if there is a B, then there is one more B in that tree, and in that simple path either they are all greens, as you can see, like all of them are green, like in that simple path, or all of them are red. If all of them are green or all of them are red, then the answer is that there is no what you can say that there is no at least like, because there should be at least one green and one red, that is like invalid tree or that invalid configuration. Hope you get the point. But if there is at least like one red or one green, like both red and green should be there, then it can happen that, let's say that there is one green and one red, then because these are nodes, as you can see, there is one node, as you can see, like one connection that is between green and red. So if there's a path between any two blue vertexes, then there should be at least one green to red or red to green node connections in this whole path, I suppose, if you get the point. Because if they're not all greens and all red, there should be at least one green and one red. So there should be at least one joining between one green and one red in the whole blue to blue path, I suppose, if you are with me. So what will happen that if I like break that out, okay, what will happen that if I break all the red and green paths, what you can see, because if that's a valid configuration, if I break all the green to red what you can say connections, then every pair will be disrupted, like they will not be connected. So if there are, let's say that this is two blues, like these are pairs of blues, they will also form a pair, let's say, and there is one connection that is between green to red, like there is one connection here. There is one connection also green to red. There's also one connection that is green to red. If I like delete this connection, obviously this whole connection will be deleted out because these are like just nodes. If I delete this connection, just only this vertex, not vertex, actually this edge between them. If I delete this, just this edge, so it will actually, what you can observe is that this will form individual components. So because this edge will not be there, this will be somewhat, and because there is also not this edge, there will be somewhat like this component. I hope you get the point, because component means that these are this, only these nodes will be there like this. Similarly, there are only these nodes that are like this, and there will be like a component like this. Got it? And what you can see here is that in this whole component there is only one B. There's only one B. There's only one B. This one B just tells that because there is a connection between G and R, if I break them out, the component that is forming, or like a subtree, whatever you can say, that is formed, that is only having one blue part. Okay, if there are multiple blue paths, so let's say that there is a path, like there is a connection between two blue pairs, like two blue nodes that are having all reds. If all of them are red, and if I break all the green and red or green edges only, then there is no red or green like red edges, because all of them are red. I will only break the red green or green red edges. So then nothing of that. So that will form a like complete one component only. And in this component there are two blue. If there are two blue, it actually means that this component doesn't have that property that the path, continuous path between two blue vertexes will be having at least one green and one red, because if that will happen, I should have broken that, and if I have broken that, that two blue should not be in the same component. I hope you get the point. And if then the same component or same subtree, it actually means that between these two blues there exists one simple path that is having no red and no, like they should not be having at least one red and one green edge vertex, I suppose, and thus that is invalid. So the whole problem now boils down to that you are given the whole tree. Let us break all the edges that are having either red green or green red on the two vertexes, and then you have some disoriented or like different chunks of components or subtree that is left with you. And in the every component you can do DFS in individual component. So let's say that there is one component like this, one component like this, one component only like this. You have all of these components. In individual component you just do DFS and check that in individual component, if there's only one blue or no blue, then it is fine. But if there are more than one blue in any of the component, then it means that that is invalid configuration, because there are two blues, which means that both of them blue should be having a case in which they are having, what you can say, like not at least one red and green edge, like vertexes, sorry, and then that is invalid. Hope you get the point. So that is the whole logic for this problem. Let us move down to the actual solution. So you can find out the code in the description of this video. So what you can see here is that this is a total, forget about that. What you can see is that the input is n number of vertexes and the string s that will tell you what is the color of every vertex in the tree. Then this is the adjacency matrix that will form the tree, and then the visited one. And what you can see is that I will take the input, because the input is such that there is a connection between, or there is an edge between x and y. Subtract one from it so that it will be from zero indexing. And because, as you can see, that I will only like add a particular edge in the tree if, as you can see, if because I'm adding an edge between, let's say, 2 index and 3rd index, I will check in that whether they will be like R and G, because I have the, what you can say, the color schema of those vertexes also, that is in the string S. I will be checking that whether if I'm connecting between X and Y, okay, if they are either R and G connection or G and R connection, okay, then I will not be connecting that, because my main motto is to form a tree such that I should not be connecting out the edges that are connecting out vertexes with RG and GNR. Hope you get the point, because that will actually like separate out the blue vertexes. and that's, or else I will just like insert them into this hole. So that is forming a like bidirectional tree. Okay, then what I'm doing is that those are individual components that are forming out. Then I will be iterating over every vertex that is doing this for loop. If it is already not visited, then I will make my total 0, which means that not visited means that I'm on a all over new component. So I will be like finding out in a particular component, I will be doing a DFS, and in that DFS I will be like marking out all the nodes in this component and checking how many blue nodes are there in this particular component, okay, or subtree. And if the number of blue nodes, that is the total after doing this DFS, becomes greater than equal to 2, which means that in this particular component there are more than 2 nodes, then the answer is that that's false, that I should not move any further. That is a altogether invalid case. Just return no and just return out. Else, if all of the components doesn't have any like less than 2 blue nodes, the answer is yes. How I'm doing that in this DFS call, what you can see is I will be sending out the string S, the adjacency matrix, as well as the visited matrix. If the particular node I am on is B, which is like blue, I will be incrementing my total. That is, I have seen a blue node and mark it as I. And for every node, because I'm iterating over this whole component, marking out every vertex that I'm on, the index of that as true, that I've already visited now, and iterating over all the edges that are connected to this particular edge that I'm on. If it is not visited, do a DFS on that. So this is just a simple DFS, okay, over that whole component. And that in the end, because I'm like appending or totaling out how many B's are there in this particular component that I am on, that is global. So that is why I'm initializing my total with 0 before starting out this DFS call over that, because that's a recursive DFS call, and it will be like this total is global, so that it will be keep on appending out, but it will only stop when I've iterated over the whole component, okay. And then this total will be storing out what is the total number of B in a particular component and printing out and checking that out. Hope you get the solution and the code for this problem. It's not too difficult, it's just simple DFS. You just have to need to build the observation part. Okay, so thank you for watching this video till the end. I will see you next one. Till then, keep coding and bye.